everyone. I'm Anish Sonar and I'll be presenting alongside my teammates Vaibhav Kannur and Aditya Shetty. Our topic is single atom catalyst for high performance metal air batteries. This presentation explores the cutting edge solution in energy storage and metal air batteries and how single atom catalyst or ACC can dramatically improve their performance. We'll walk through the current limitations of metal air batteries, advantages, and the future prospects of this exciting field. Next slide. Yes. So metal eye batteries are gaining global attention as next generation energy storage devices. They work by using a metal anode such as lithium, zinc, or aluminum or iron and oxygen from the ambient air as well as cathodic reactant. There are three major reasons why they are promising. So, firstly, we have a high energy density. For example, lithium ion batteries have theoretical energy densities that can exceed those of current lithium ion batteries by multiple times. Second, cost effectiveness. These batteries utilize abundant and cheap materials, minimizing the dependency on rare and expensive materials. Eco friendliness. They involve non toxic materials and are more recyclable, the environmental impact. All of this makes metal batteries ideal for future applications in the electric vehicles and also renewable energy storage. Next slide. Next up, we have the challenges of metal batteries. So, first, they have a very shorter lifespan. Over time, corrosion and formation of metal oxides or byproducts on the electrodes degrade their performance. Second, rechargeability is an issue. Some types, like aluminum air batteries, are not that easily rechargeable and often require the anode to be physically replaced. Third, their performance is highly sensitive to air quality. Moisture, carbon dioxide, and other pollutants in the air can affect their reactions at cathode, reducing the battery's efficiency and stability. Addressing these issues is essential before we can consider the large-scale implementation. Next up, we have Vaibhav Kannur, who will be leading this presentation.
Okay, so one of the core challenges in improving metal air battery performance lies in the catalyst used to drive the chemical reactions. The traditional conventional catalysts, often based on precious metals, face several limitations. The stability. Over time, the catalysts degrade due to sintering or leaching, especially under harsh operating conditions. And the next, environmental health concerns. Some catalysts contain toxic, hazardous materials. Also, the cost and availability. Platinum group metals, for example, are effective but are very expensive and extremely rare to find. And the selectivity also. They can lead to undesired side reactions and byproducts which lower the energy efficiency. Clearly, there is a strong need for a new class of catalysts that can offer better durability, low cost, and higher efficiency. This brings us to the single atom catalysts, or SACs, an exciting breakthrough in catalysts. SACs involved disappearing individual metal atoms on a support material, often made of carbon or metal oxides. So, what makes SAC revolutionary is maximized atom efficiency. Every single metal atom is utilized as catalytic side, which means no precious metal is wasted. Enhanced selectivity and activity. The uniformity of active sites allows precision control over chemical reactions. Bridging homogeneous and heterogeneous catalysts. SACs combine the best of both precise control and solid support. Application versatility. SACs are already being researched for hydrogen evolution, nitrogen fixation, CO2 reduction, and now metal air batteries. They are not only effective but also economical in the long run. Oh, okay, so the synthesizing SACs require highly controlled techniques to ensure individual atoms don't clutter together. These are some of the three main strategies. The atomic layer deposition, which is also called ALD, a vapor phase method that allows precise layer by layer atom placement on the support. It ensures uniform distribution and high stability. High temperature pyrolysis. Here, the metal containing precursors are thermally treated, forming strong metal support bands. It enables high loading of the metals, atoms, and work with various materials. The wet chemistry and self assembly. This involves solution based synthesis, where molecular templates guide the formation of the active sites. It's cost effective and scalable. Each of these techniques contribute to SAC's reliable and commercially viable for battery use.
Okay, catalytic mechanisms ORR and OER in the metal air batteries, two fundamental electrochemical reactions occur at the air cathode. There is oxygen reduction reaction happens during the discharge. Ideally, 4 electron pathway is desired, where O2 is directly reduced to water. This route provides the higher energy efficiency compared to that of the 2 electron route, which produces the hydrogen peroxide, a less desirable product. And this oxygen evolution reaction happens during the discharging, which involves the oxidation of water into oxygen gas. OER is typically slow and energy intensive, and SACS improves these reactions by offering a better electronic configurations at the active sites and lowering the activation energy and speeding up the reaction rates. This makes them highly valuable for enhancing the battery performance. Next slide. SACs in metal batteries, battery systems. So let's look how the SACs are applied in the actual battery systems. In zinc air, batteries, SACs like Fe in C, and there is the iron nitrogen carbon and cobalt nitrogen carbon function in the as a bifunctional catalyst, meaning they are effective for both ORR and OER. This addresses the issue of a slow reaction kinetics in the alkaline conditions. In lithium-air batteries, SACs which helps in reducing the high OR potential required for the decomposing lithium oxides during the charging, which improves the energy efficiency and cycle stability. These examples prove that the SACs are not just theoretical, they are already enhancing the real-world systems. Next slide. The performance comparison and implications. This table gives the comparative view of different metal air batteries. Like a lithium air battery have the highest theoretical energy density. They differ from very high OER and higher potential values and with a limited cycle life. Zinc air batteries, while they have the lower in energy density and more commercially viable due to the better cycle life and the lower cost. Sodium air batteries lie somewhere in between, offering a balancing but struggling with the chemical stability and byproduct decomposition. From this, we can conclude that while lithium air is the ultimate goal, and zinc air batteries are likely to be stepping stone in the.
Looking ahead, there are several promising directions in SAC development. Improved stability and metal loading. Researchers are exploring polymer encapsulation and new supports to avoid atom aggregation and leaching. Bifunctional electrocatalysts. Advanced strategies at the atomic scale are being developed to optimize SACs for both ORR and OER. Machine learning and AI. These tools are accelerating catalyst design by predicting optimal structure and conditions. Advanced characteristics techniques in situ and operando spectroscopy methods help us observe how SACs behave under real battery conditions, leading to better design principles. These advances can make SACs not just a lab curiosity but a backbone of future battery technologies. To wrap up, single atom catalysts present a transforming approach to overcome and major limitations of the metal air batteries. Their efficiency, selectivity, and cost efficiency can redefine how we can store and use energy. With advancements in synthesis techniques, machine learning, and battery design, SACs have the potential to make sustainable, high performance metal air batteries a reality. Thank you for your attention.